And so my recording will be the one, and we won't have a problem. We usually don't. So everyone mute your sounds. And I will now introduce our distinguished guest speaker to this May 3rd Hard Science Fiction meeting. Chris Impey, a friend of mine and of my husband's for many years, and a distinguished astronomer at the University of Arizona's Stewart Observatory and Astronomy Department. So Chris has covered many areas in his work. I'm sure he'll tell you more about that. They all have to do with stellar astronomy rather than planetary, or most of them have to do with stellar. But now that we're getting into astrobiology, I guess that crosses the line. So with that kind of awkward introduction, Chris, I'll hand it over to you.
Okay, I'm pleased to be with you and present to this group. It's a topic of interest, or the hard science fiction arena is of interest to me. I've been at the university quite a while. I work on observational cosmology, actually, so most of my research is distant galaxies. So if it's closer than 1 billion light years, I don't care. But astrobiology is all closer than that, so I care. I like astrobiology, and I've been dipping my feet in that quite a lot. I've written 10 books and 1 science fiction novel, and I'm working on a book on the periodic table right now. But today I want to talk about how the science of astrobiology can inspire science fiction. But I'll start with one arena where the sort of science fiction was leading the science and sort of got it wrong, because in astrobiology currently, it's sort of the opposite way around. The science is so out there and exotic that I think it should be inspiring science fiction writers to really think out of the box as they write about this stuff. Well, I'll start with a nearby test case of Mars. All right, with Gustav Holst to set the scene and the mood. We know that in the case of Mars, the imagination was well ahead of the science for what Mars could support, basically. Percival Lowell imagined linear features on Mars. At the time, he was using one of the world's largest telescopes on the best site in northern Arizona, so no one actually could confirm his claims. He was using naked eye observations, and he was wrong. It was wishful thinking, fanciful. There are no linear features on Mars. There are no canals bringing water from the poles to a dying civilization at the equator. But it sort of unleashed the popular books that he wrote about this, of course, reached a wide audience, and this unleashed the expectation that our neighbor planet would indeed be inhabited. And then very similar in time, we have H.G. Wells and science fiction sort of really cementing the idea of Martian civilization, in this case with a malign intent towards the Earth. And then as we move into the 20th century, it goes into the sort of pulp fiction, pop culture arena. Edgar Rice Burroughs and the imagination of sort of buxom princesses and muscular princes fighting creatures on Mars, or a fully visualized world inhabited. And then going towards the Second World War, on the cusp of the Second World War, the famous War of the Worlds broadcast by Orson Welles, which fooled a lot of people. It was very artfully done. He was a masterful impresario and director, of course, eventually. This was his theater company, the Mercury Theater Company, that spawned many famous mid-century careers of actors. And the set piece here was supposed to be a dance music concert, which was sequentially interrupted by radio bulletins of the descent of a alien spacecraft landing in New Jersey, and then the investigation of that. And so you get a flavor of it with a couple of clips.
Ladies and gentlemen, we interrupt our program of dance music to bring you a special bulletin from the Intercontinental Radio News. At 20 minutes before 8 Central Time, Professor Farrell of the Mount Jennings Observatory, Chicago, Illinois, reports observing several explosions of incandescent gas occurring at regular intervals on the planet Mars. The spectroscope indicates the gas to be hydrogen and moving toward the Earth with enormous velocity. Professor Pearson of the observatory at Princeton confirms Farrell's observation and describes the phenomenon as, quote, like a jet of blue flame shot from a gun, unquote. We now return you to the music of Ramon Raquello, playing for you in the Meridian Room of the Park Plaza Hotel, situated in downtown New York.
Now, Wells did issue a disclaimer. So at the beginning of this show, there was a disclaimer that saying that it was fictional and pretty much saying what was going to happen. But if you missed the first couple of minutes, you just came into the dance music and then you heard these sequential interruptions, and they occur with increasing frenzy and panic. And so 15 minutes later, with people already going outside and starting to pack up their cars in anticipation of an invasion, we have this.
Ladies and gentlemen, am I on? Ladies and gentlemen, here I am, back of a stone wall that adjoins Mr. Wilmer's garden. From here, I get a sweep of the whole scene. I'll give you every detail as long as I can talk and as long as I can see. More state police have arrived. They're drawing up a cordon in front of the pit. About 30 of them. No need to push the cars back now. They're willing to keep their distance. The captain is conferring with someone. Can't quite see who. Oh, yes, I believe it's Professor Pearson. Yes, it is. Now they've parted, and the professor moves around one side, studying the object, while the captain and two policemen advance with something in their hands. I can see it now. It's a white handkerchief tied to a pole. Flag of truce. If those creatures know what that means, what anything means. Wait a minute, something's happening. Some shape is rising out of the pit. I can make out a small beam of light against a mirror. What's that? There's a jet of flame springing from that mirror, and it leaps right at the advancing men. It strikes them head on. The logs are turning into flames. He's followed by the woods of fires. The gas tanks of the automobiles spreading everywhere. Coming this way now, about 20 yards to my right.
And I paused because what Wells did at that point was he left 15 seconds of dead air, as it's called in broadcasting, just silence. You never do that in broadcasting. You always babble if you're a commentator or say something. You don't leave dead air. He did it, of course, for a very great dramatic effect. And so this was, cementing the idea that Mars had malign aliens on it. And it took another few decades before space probes, the Mariner being the first space probe to Mars, orbiters, landers, eventually rovers, showed us the real Mars. Now, the real Mars is a little less exotic than the science fictional Mars. It's a beautiful place, though. And we have now all these history of the science fiction involving Mars. My personal favorite, Martian Chronicles, of course. The Red, Green, Blue Mars trilogy of Kim Stanley Robinson is really great because it's visioning terraforming Mars in the future and a separate separate civilization of humans eventually branching off from the human tree and rebelling against the home planet overlords. So that's a beautifully realized book, also written with incredible accuracy about the geology and topology of Mars. And we're talking about books here, but of course, Mars got into the movies too, often in a comedic, sort of horrific comedic way. You can pick your favorite sort of pulp fiction type movie about Mars. There were a number of them. But the real Mars is a little different. It is beautiful, though. So Mars, we think, is dead, at least on the surface. It's a very thin atmosphere, of course. It's have no magnetic field to protect from high energy radiation. UV pours in, and it's essentially sterilized, the top centimeter of the regolith. It does leave open the possibility of subterranean life. And so we've had rovers rooting around for a few decades now, looking for indirect signs of life or signs of life in the 3 billion-year-old Martian oceans that we know to have existed when Mars was warmer, wetter, and had a thicker atmosphere. So that's a little disappointing compared to the science fictional vision. And we may not know the answer very soon. Our sample return, which was already struggling with a busted budget, well over $10 billion, is in the crosshairs of the Trump administration with the NASA cuts. So it's very unlikely to survive the next budget cycle. So it's going to take us a while to answer the question of life on Mars, or rather under the surface of Mars. We will eventually, if Elon Musk has his way, and maybe even without Elon Musk, eventually have habitations on Mars. And that would allow us to fully investigate the planet. This may happen through the private sector, people like Musk, or actually will happen more fruitfully, I think, by the Chinese. The Chinese are rapidly overtaking the United States as the spacefaring superpower. They're investing more heavily in it, especially given current budget constraints. So we will have a Martian colony at some point, I think decades in the future. And that has some science fictional aspects, of course, because I think apart from the modification that will happen over generations as people are born and grow in a environment with low gravity, purified air, very special diets, I think these technology forward colonists will use radical techniques of genetic alteration to adapt themselves to this new environment. They'll use medicine with nanobots. They'll essentially follow the cutting or the bleeding edge of our medical technology as just a way to live, using all of these technologies, maybe hacking their own genomes, 3D printing tissues, bones, and organs to do their own medicine. And that's some interesting experiments that are going to take place on Mars. Maybe not in the next 10 or 20 years, but maybe 40 or 50 years. So let me move to the real world of astrobiology. And the world of astrobiology is dominated by exoplanets and the incredible discovery rate of exoplanets. This is a visualization, of course, of the over 7,000 exoplanets that are known to exist. Only a few hundred, 150 about, have images made of them. And they're just dots, they're single pixels. We don't have the resolving power to see a planet at distances of light years. And so these are just imaginations of the planets. We only really measure the mass or the size of the planets by indirect methods. The discovery rate has been prodigious. And in this graph, we'll see how the number has grown since 1995. And it's an exponential growth rate, driven primarily by the Kepler telescope. And if you analogize that, the only technology that's had similar prodigious growth rate is basically our cell phones. But that's remarkable to have a sort of technology of detection in space that has an exponential rate of progress. That's not usually how science technology works. So it's been an incredible series of decades and discoveries. We now know what the populations of exoplanets are, and many of them are unfamiliar. We live on a rocky planet, of course. In this orbital period and size diagram, the Earth is off to the right of that yellow shape for rocky planets. It's at the edge of our detection capabilities, but Earth-like planets have been found. But most of them are not Earth-like planets. Most planets are either super Earths or ocean worlds or ice giants or sub-Neptunes, whatever you want to call them, in the blue area. And there's a lot of very hot planets too, either small rocky planets very close to their star, lava worlds, or hot Jupiters, which were really the first type of exoplanet to be discovered because they were the easiest type to discover with short orbits and large masses. So this is the terrain of exoplanets. And if you want to inspire science fiction, you just have to take some of the most exotic examples and just visualize or imagine a story built around each one. Say, what civilization, what species could possibly utilize such a planet, live on it, adapt it to their purpose, and what would that look like? Because these are quite wild, and I'll just give you a few examples in quick succession. We have found the Tatooine planet, the double star planet visualized in Star Wars. That's not science fiction made real. There's a planet WASP 76, which is one of those lava worlds, and it has on its hot side, it's tidally locked to its star. So the hot side is incredibly hot, and it's essentially melting metal from the planet's surface and vaporizing it into space. It goes to the far night side of the planet, and it rains down as iron molten droplets. That's a wild world for sure. And there are not a couple of these. There are hundreds of these. There's another world, which is a larger world, a super Earth, and it has a silicate material. It's also kept very hot by its parent star. And that silicate material is thrown up into the atmosphere where there are supersonic winds. And that rains down molten glass essentially on the far side of the planet. I'm not sure if that makes it habitable or completely uninhabitable. Another interesting world. We have planets that are black as coal. They absorb essentially all the radiation that falls on them. They could have subsurface oceans, and so in some sense, even a planet like this could be habitable. Here's an example of a very fast orbiting lava world, which orbits its star in about 1.5 days, I think. It's almost the most rapid exoplanet known. Again, not sure what use that is as a prop or a tool in science fiction, but you could possibly imagine someone using that as a mining station because these are very rich in metals and they're easy to mine and the gravity's weak, so you could get it off the planet and purify it and send it back to your home base. There are plenty of water worlds. Water is an abundant molecule in the universe, so the Earth is not unique as a watery planet. We have found planets with 10 times the Earth's ocean, hundreds of times the Earth's ocean's inventory of water. And there are many of these. They're typically 2 or 3 times the mass of the Earth, 1.5 or 2 times the size. And they are sometimes fully covered in water, so truly ocean worlds. And that's a fascinating thought as to what might evolve on planets like that had no land surface. There are planets that are being eaten by their stars as we watch. That's an extraordinary thing. We've seen a couple of these now. They're literally being ripped apart, and then they're going to fall into their stars, and we can see it in real time. We found super Earths, that is definitely a habitable category of planets that have just been born. So they're very young. The oceans are barely condensed from steam. And again, we don't know how long it takes for a habitable planet to become inhabited and develop life. And we don't even know if it happens all or most of the time. But we can also tell stories about how planets get started and how civilizations and life get started on planets. And you should remember that there is enough material, there's heavy elements in water in the distant early universe for an Earth clone, a full clone of the Earth. We haven't found an exact clone, but imagine one. That could have formed 8 billion years before the Earth formed. So whatever's happened on the Earth, you could have an 8 billion year head start. And that's a mind-bending thought as well. You have planets with extremes of day and night, especially the ones that are tidally locked. And like Mercury, these extreme planets do have a terminator. They have a region of temperate temperatures we could survive at the boundary between the extreme hot and the extreme cold. And because there are many close orbiting planets that are tidally locked, and some of them hold significant atmospheres, there are a number of these worlds too. That's not an unusual scenario. We even have planets orbiting dead stars. The first planet to be discovered, and those people you could say were robbed of a Nobel Prize because they found a pulsar planet 6 years before Killos and Mayor found 51 Peg and got a Nobel Prize for it. We have now more than a handful of planets found around pulsars. Nobody really understands that because these are the corpses of stars that died as supernovae. And it's thought that the cataclysm of the star death would take away enough debris that there would be nothing left to form planets. However, planets do exist around pulsars. That's another interesting thought. What would a civilization see, or what would they do in the knowledge that they orbited a neutron star, essentially, and what would that look like? We have planets floating through deep space that we found by microlensing. So planets do not always have stars. They can be ejected from their stellar systems. Simulations suggest that as many as a third or a half of all exoplanets in systems as they form are ejected in the chaotic early phases of evolution of the system before the orbits settle down. And that means there are a lot of free-floating planets in space. They're very hard to detect because the two standard indirect methods of Doppler and transits don't work. So you have to use microlensing, statistical method actually. But those methods do indicate that there are a lot of these rogue planets or free-floating planets out there. It's another interesting thought. What life could be on a planet like this? They can be big enough to hold an atmosphere, to have plate tectonics, to have thermal heating. And obviously life doesn't need a star because life on Earth doesn't need sunshine or photosynthesis. So we have plenty of examples on our own planet of how you don't need a star. So here are a set of planets where there is no star. And there's a lot of time, of course, because the lifetime of these planets and life on them is not bounded by the lifetime of their star. Whatever good, bad, or ugly happens on the Earth, the sun will go red giant in 4 billion years, 4.5 billion years. These stars have no such limit because they're not limited by the lifetime of a parent star. We have beautiful planets in synchrony, orbiting in very interesting ways. The TRAPPIST-1 system is perhaps most familiar to people, but this resonant chain in the TOI 178 system, these are the ratios of the orbital periods, and they're in harmonic resonance in ratios of 18 to 9 to 6 to 4 to 3. An extraordinary, beautiful expression of Kepler's harmony of the spheres. We have planets that we think are made large part of silicates, but in many cases, the temperature and pressure have created diamond-like material. So if you want to be a diamond miner of the far future, there are exoplanets that will give you an extraordinary haul of diamonds. And then last, I'll give an example of the planet in an extraordinary situation. This is a visualization of a planet orbiting the supermassive black hole at the galactic center. The picture is of Gargantua from the movie, of course, but the black hole in our center of galaxy is not as big as Gargantua, but we can imagine what that would be like to be on a planet at a safe distance from the event horizon orbiting a supermassive black hole. And such planets clearly exist. We already know they exist. So that's just a snapshot of the kind of things that are out there. Here's a visualization, say, of a water world, a fully water-covered planet. And we should bear in mind that given there are so many water worlds, astronomers are looking for life in the universe, of course, mostly microbial, by inspecting the atmospheres of exoplanets like the Earth to see if they've been altered by biology, as the Earth's oxygen indicates biology on the Earth. But there could be intelligent life as well. SETI is only looking for signatures of radio transmitters and lasers pulsed through the universe. But that's a very anthropocentric way of looking for intelligent life. The Earth has creatures like orcas and dolphins that are pretty intelligent by any reckoning. And on the water worlds of the universe, these creatures, there's no land surface. A supremely adapted creature like an orca on the Earth in a water world could be highly intelligent, social, it could have a civilization. They will never build spaceships or telescopes, and so we won't know their existence, but we can imagine what they might get up to. And there are these nomad planets that are wandering freely through space, and we know so little about them that this is a fascinating area for science fiction conjecture. So the census of these planets is now coming in. We haven't completed these surveys, but Kepler did an enormous amount of work in filling in our picture of exoplanets. And we know there are more planets than stars in the Milky Way overall. And there's 300 billion stars in the Milky Way. So that's a pretty impressive number. And in this histogram, you can see what fraction of stars have at least one planet of different types. And you can see that Earth-like planets are not the most abundant category. There are more super-Earths and mini-Neptunes than Earth-like planets. And the solar system turns out to be unusual. There's no planet between Earth and Venus mass, which are almost the same, and an order of magnitude larger to Uranus and Neptune. But the most abundant planets elsewhere in the universe seem to be intermediate. And many of those, especially the super-Earths, are quite likely to be habitable. And as I mentioned, there's categories of habitable worlds or planets. There are the nomads that I talked about that are ejected from their systems. There are also exomoons. That's just a great technical challenge to detect exomoons. Obviously, Avatar was a good movie about life on an exomoon, directed by Jim Cameron. We have not yet firmly detected any exomoon, but we know exomoons exist. I mean, logically, giant planets around other stars will have moon systems like our giant planets do. And if you're talking about how many habitable places there are in our solar system, there's Earth, of course, there's Mars on the edge of habitability, and then there's about 10 or 12 habitable spots, I'll call them, and that is outer moons of outer planets. Some are very familiar to us, Europa, Enceladus, Titan, and the others are in the further out solar system, moons of Uranus and Neptune, which we really haven't visited very much, just a couple of space probes over decades. They have subsurface oceans, and they, again, could be habitable. So in one solar system, ours, where there's one habitable planet and 10 times more habitable moons, you have to imagine that exomoons are going to be places where there's a lot of life in the universe. And we know nothing about them scientifically because they're just too hard to detect. They will be detected soon. I think the techniques are advancing that we should be detecting exomoons very soon, actually. And the numbers are prodigious, of course. The number of habitable worlds in the galaxy, that is, Earth-like planets at the right distance from their sun-like star to host liquid water, is about 10 billion. That's like the number of grains of sand in a child's sand pit. I think it's quite a large number. Astronomers get blasé about big numbers, but you have to visualize each of these as a world that you could inspect. Each one has a story to tell. Many of them may be living worlds, and there's tons of time. It's not just the real estate of planets themselves, it's the real estate of time for things to happen. As I mentioned, Earth-like planet starting 8 billion years before our Earth. The Earth is our solar system is a late arriver in the universe, an old universe. And then in the universe as a whole, since our galaxy is typical in every way, it's 1,000 billion habitable worlds. And my countryman, I lost my Scottish accent long ago, but my countryman Thomas Carlyle put this nicely: if they be inhabited, what a scope for misery and folly. If they not be inhabited, what a waste of space. So as raw material for science fiction goes, you couldn't get better than 1,000 billion habitable worlds in the universe. Everyone should be able to have fun with that. And I'll finish with a few comments about weird life. Much science fiction, inevitably, especially in the popular culture, not so much in books, but certainly in TVs and movies, is highly anthropocentric. It views extraterrestrial life through the prism of the Earth and imagines humanoids and, creatures that are essentially similar to us, except in superficial ways. And that's clearly not imaginative enough to encompass what the universe has likely provided. And I don't know that science can actually help us here because we only know of one example of biology. But I'll make a few comments about weird life as far as it goes. First of all, the diversity of life on Earth is just one biological experiment. Here's the tree of life represented in RNA, so genetic distance from the last common ancestor at the bottom, at the root, 4 billion years ago. And you can see that the real estate of life in genetic terms, this is genetic map where real estate is marked out in deviations of RNA or DNA. This is a microbial world. We live on a microbial world. There are millions of times more species of microbes than plants and animals. And most of them are very poorly studied. They're very hard to culture in the lab, and there's no motivation or commercial reason to do so. So we just don't know about them. And you can see plants and animals over to the right. And apes, us and our primate cousins, are smaller than the dot on the eye above animals. So we think we're quite impressive, but we are just the tiniest little twig in the tree of life. It's mostly a microbial tree of life. So we have to go beyond Darwin. Darwin theory of natural selection could well apply on other planets. It has some plausible principles behind it that we can imagine generalized beyond the Earth, but we don't know. So we're sort of bound to speculate, and this is from scientific perspective, but science fiction can speculate even more broadly using this as a basis. You could have microscopically weird life where different amino acids or base pair sequences, and there are labs on Earth that have already altered the genetic code. It can be done, and it makes a viable organism. So it's just a choice that biology made in the evolution of life on Earth, and other choices could be made, and the life would be somewhat different. You can have more weird, where you go away from the so-called central dogma of biology, the triad of DNA as the information storage, the vault of genetic information, RNA as the carrier, the transcription, and the expression of the creature's function and form in the protein sequence. That's not the way it has to be. That's the way it is on Earth. And we can imagine other microscopic or molecular architectures for life. You want to go weirder still, you can try non-carbon life, non-water-based life. The biologists, or the chemists rather, weighed in. Silicon life is a popular trope in science fiction. And silicon is, of course, located in the same column of the periodic table as carbon. It has similar chemical properties. But the biochemists now have studied it in detail in the lab for decades. And silicon does not form as long, stable, and complex chains as carbon. It's just not as good for information storage as carbon. That's not to say it couldn't happen out there, but it's not the best by far. So yes, possibly silicon-based life, but carbon is abundant and probably will be utilized. The solvent, though, is quite up for grabs. It doesn't have to be water. For biologists, water is a double-edged sword because water obviously dissolves chemicals and facilitates interactions, but it's also corrosive. It dissolves those same chemicals. And to biologists, water is, kind of toxic to life as well as facilitating it. And so you could have quite a wide set of potential solvents. I've seen papers that have speculated about dozens of things like ethane, methane, cleaning fluid. You can think of all sorts of things, sulfuric acid even, which sounds implausible. There are many possible solvents for life if you assume it needs a liquid medium to facilitate interactions. And then to go very weird, you just have high density biochemistry. We think life is efficient. The information in a single human cell, genetic information, is about the amount of information on a DVD. That seems pretty dense packing, but it's not. You can have millions of times denser packing of information held in molecules if you had different architecture. And that means you could have scaled down versions of life, dramatically scaled down versions of life that are just as functionally complex as our form of life. That needs consideration. And if you go up to the large scale, again, you can have a lot of variations. You can go a little bit weird. Humans contain about 50 different cell types, but that's just an arbitrary number out of evolution. You could have different cell types and a wider diversity of them and so on. You also could have gene swapping at a higher level than has happened in the history of life. History of life involves mostly slow evolution by mutation and sexual reproduction, sharing of the DNA. But there's also been instances where life has involved larger packet sharing or switching of genetic material, and that accelerates evolution and creates new possibilities. So if we imagine that kind of symbiosis or gene or organism swapping occurring on larger scales or in different ways, you could have a very interesting evolution of life. And then why do you need a cell as the basis for life? That's what life on Earth is. But people have conceptualized theoretically, you could have a network, a chemical network as opposed to a container. We think, for example, that life may have got started without a cell deep underwater, hydrothermal sea vents, where the pore space of rocks becomes the container for the first biological material. So you're actually using pore space of rocks rather than a cell as a container. So you don't need that model. You can have different models. And if you, again, play with this idea, you can imagine that microbial organisms working cooperatively, which they do. Communal sensing is a common feature of bacteria. You could have planet scale terraformation or architectures or geoengineering conducted by microbes, conducted by organisms not as big and sophisticated as we are. It's totally plausible. And this is scientifically plausible. Science fiction should be able to take it from there and take it in all sorts of interesting places. We also know that we've had exponential progress and we are approaching what many people think is the cusp towards post-biological evolution. These are the gains in AI systems approaching human levels of capability. And you can see that in their different capabilities, they've accelerated. It took image recognition 5 or 6 years to approach human levels. The language models have approached human levels in just a couple of years. And this is a double exponential. It's nothing like Moore's law, of course. This is a fantastic gain. In the last 5 or 6 years, 10 million times computational capability over the doubling time of essentially 2 months. It's breathtaking. And if you want to compare it to what you get with a machine, so take that computational capability, apply sensors to it, and put it into a little robotic organism. Imagine you have these exploring Mars, little robotic ants or whatever. Miniaturization helps you. And if you look at the progress of computation and then put that computation in a package with sensors and say, how sophisticated is the robot compared to terrestrial life form, you'll see that the best robots on Earth are something like a lizard or a mouse. And that seems right. They're not that impressive. They're quite impressive, but not that impressive. But on this trajectory, we are projecting to human levels of computation or thought and robotics or behavior in maybe 20 years. 10 is probably optimistic. And looking along the right-hand side of this diagram, what's dramatic here is that computational capabilities have evolved in a few decades what took life on Earth 3 billion years to evolve. That's the degree of acceleration of the machines. And so if this is happening on the Earth around us as we speak, post-biological evolution, it will be foolhardy to imagine that we're the first or the only or the most advanced. And so the universe indeed could be, and this is of course well known in science fiction and well utilized, the universe could be filled with flesh and blood organisms, creatures like us or more advanced than us, but it could well be filled with AIs and bots and maybe more dominantly filled with machines than with flesh and blood organisms, because the machines have obvious benefits. It's very unlikely we're going to leave the solar system with humans in the next century. It's just too hard. Energy costs are too high. We don't have suspended animation. But you can do it with the nanobots probably in the next 10 or 20 years. So that's the way the Earth is going, and we have to imagine that will play out elsewhere too. We do like to think of ourselves in a particular way when we contemplate our place in the universe, and the aliens don't necessarily have to agree with that. They may think of us a different way. As far as visualizing these futures and utilizing them in fiction, it's interesting to make simple analogies. The technology analogy is useful. It took 50,000 years on Earth to go from arrowheads to smartphones. And you need to try and imagine what is to a smartphone as a smartphone is to an arrowhead. And that's where we'll be in 50,000 years. I think it's very hard to do. Even creative people would have trouble wrestling with that. And then in evolution terms, it took a billion or so years, a couple of billion years to go from microbes to humans. And again, since you could have an Earth clone with 8 billion years head start on us, you have billions of years of evolution to play with. So what is to us as we are to a microbe? That's also very hard to imagine. But we're duty bound to imagine it, and we're duty bound to turn it into fictional accounts. So with that, I will leave you and open floor for questions.
Well, Chris, there's been a lively debate and discussion going on with Bob contributing lots of dire posts in the chat about what we might be approaching the great filter and everything. But other people have been posting. Let me go back and see if there are questions. You can check in the chat as well.
I just opened it up.
Okay.
Okay, it's taking me a while to scroll down here.
Emad has a question there.
Yeah, while I'm scrolling, you can just read one out if I can't.
Okay, is it true that life on Earth originated on Mars, a dry world, because water is corrosive to RNA? From Emad Aisha.
Yeah, I mean, of course, we have to leave the door ajar for us being Martians for the simple reason that there is an inefficient interplanetary transport in the solar system. And from a low mass planet with a thin atmosphere, it's easier to get a rock inward to the Earth than it is the other way around. So it's much easier to get a Mars rock to the Earth than it is to get an Earth rock to Mars. So if there was life on Mars 3 or 4 billion years ago, it is indeed theoretically plausible that a life-bearing Mars rock could have made it to Earth and seeded life on Earth. But the biologists and the people who study the history of life on Earth and simulate it in the lab do have plausible pathways for forming life on Earth. So I don't think we need to jump to that hypothesis, and there's no direct evidence for it, of course. If we brought back Mars rocks with microbes in them, or eventually got genetic evidence of Mars life, we would find out instantly whether it was identical to us or different, and that would be an amazing discovery. But people who study the origin of life on Earth do have some big challenges because the evidence record is so patchy given how few intact rocks survived from 4 billion years ago. But they do have plausible scenarios for how life started. And water, despite its being a double-edged sword, does facilitate life. And the experiments people do in the lab get you fairly far along the road to a cell, which is to say they get you to 1,000 or 2,000 atoms long chains of RNA, and then you can template the RNA on clay particles inside vesicles. So there's cute little models that sort of play out how that may have happened.
I see another question from Del Gordon. Professor Impey, your paper with Ron Joseph on extraterrestrial life in the thermosphere mentions dusty plasmas as representing possible forms of life, or at least lifelike behavior. Is there any further research planned or being done by the University of Arizona in this area of dusty plasmoids in the thermosphere?
Right. So that was I'll call it an interesting collaboration, because I was on this paper and I didn't sign off on everything they said, and I had to moderate a lot of the language because the speculation got a little crazy. But it is no doubt that the behavior of electromagnetic plasmas in the atmospheres is very interesting and complex. And like people who study life on Earth, for instance, talking about intelligence of cetaceans or things like that, I would try and be scrupulous about distinguishing between behavior and intelligence. We're pretty much sure that cephalopods, octopuses, have complex and very interesting behavior, and therefore they are probably intelligent. Plasmoids in the atmosphere, I'm not willing to make that connection, but the behaviors are very interesting. So I just put it in the category of worth for further study. And to answer the question, it's a very difficult arena for study because replication is a core of science. That's how science moves forward. People have to be able to reproduce results. And many of the things, we can talk about ball lightning if you want another example, where it's just been historically very hard to reproduce results or replicate them in the lab, for example. And that's basically the case with these plasmoids. So no, not to my knowledge there's 2 people in the physics department who may be interested in this, but I'm not actively involved in an investigation like this anymore.
I see another comment, and there's a question from Del Gordon. Plasmoids a kilometer long are extraordinary. We could devise experiments using space tethers to replicate and research this phenomenon. The cost of a mission to Earth orbit would be less than lunar or planetary missions. Could the plasmas in the thermosphere represent a heretofore undetected shadow biosphere, maybe life as we don't know it?
Yeah, and again, I'm too heavily trained as a skeptical scientist to jump there. I just settle on the fact that it's complex and very interesting behavior. It's very complex physics as well. Even the physics is not fully understood because you're dealing with electric and magnetic fields and plasmas, and that's just a tough subject. So a shadow form of biosphere life as we don't know it, that would be a conjecture, and you could maybe propose experiments that might test that. We're not close to that kind of a test. I'll mention that the whole idea of a shadow biosphere on the Earth has been in play in astrobiology for decades, because we know there could have been multiple starts to life. We know the Earth was a hostile place as life formed roughly 4 billion years ago. Then there was a late heavy bombardment, could have sterilized the planet. So it's entirely possible there were multiple independent starts for life. And so some biologists have speculated about a shadow biosphere deep underground. The bulk of biologists, though, don't like that hypothesis because they just point out that on the Earth, and we'll not talk about the atmosphere now, if there are multiple biological experiments, it would be very artificial for them to be totally and eternally sequestered from each other. And if they interact, then the nature of evolution and natural selection is that the most successful organism outcompetes all the others, and the other organisms become food for the successful one. So biologists will say they don't like the shadow biosphere on the Earth because they think even if it existed, in the end, it would have been consumed by us, the most successful single biological experiment. In the atmosphere, all bets are off. We do know there is life in the upper atmosphere, where there have been studies of microbial, shielded from radiation, spore-like entities in the upper atmosphere. And we're not talking about intelligence or complex behavior. We're just talking about microbial life that's lofted into the high atmosphere, the stratosphere, and it exists there. And that's interesting. So there is life in the upper atmosphere, but it's not complex in its behavior.
I see that my husband, Bob, who's been giving us the whole stream of science fiction bibliography to go along with everything you're saying, says that Hal Clement wrote stories about a whole zoo of weird life on weird planets. Bob, would you like to say a couple words about what those were?
Well, it's been decades since I've read those, but I remember a weird life on a planet of very high gravity that was spinning really fast, and the gravity increased as the creatures went to the pole. And collaborations with the human civilization to study their planet and tell Earth scientists about it and so on.
Yeah, that's interesting. And I know there are physicists who've written speculatively but plausibly about life on a neutron star, and a sort of very miniaturized life in an intensely high gravity environment. It's fanciful, but it's not. It doesn't break the laws of physics, actually.
Okay, we got a couple more from Del Gordon. Because an example of life as we don't know it is needed for a universal theory of life, finding an example of life as we don't know it in Earth's own thermosphere could be a revolutionary scientific breakthrough. Comments?
I definitely agree with the premise that we do not have a universal theory of life. We have a sort of incomplete theory of how life on this planet started and evolved, and that's all. And that's why we're really hustling hard to find life elsewhere. And indeed, it seems like the Earth's thermosphere is the most proximate environment to investigate. There's not a lot of active investigation. There are not a lot of missions, and actually with the evisceration of NASA's budget that's planned by the current administration, these kind of experiments and projects are almost certain not to get funded. They're just not core enough to NASA's mission or favored enough. So I think the two places where we could look for life as we don't know it are, of course, exoplanets, because we are going to be inspecting the atmospheres of exoplanets, and that will be an indirect measure of a metabolism by the product of a gas that occupies the atmosphere. It could be methane, it could be oxygen and ozone, of course. There are other biomarkers, as they're called. So we're going to be looking for those. That's a very broad brushstroke, though. It doesn't tell you anything about the detail of the metabolism. It just gives you a byproduct, essentially. And then probably the favored example of life as we don't know it in the solar system is not Mars, but is Titan, because Titan has ethane, methane seas, shallow seas. It's a very cold planet, but there's geothermal, there's cryovolcanism in those waters, so it's tepid. It's ethane and methane mixed with a little water and a little ammonia is a plausible solvent for a very weird form of life as we don't know it. So Titan is staring us in the face as the place we would look in the solar system for life as we don't know it. And it's just very slow to get missions, life detecting missions out there, although there are a couple that are planned.
Okay, and we have another question from Del Gordon, and he wants to know what you're working on yourself currently, or what do you want to research in the future?
Well, I mean, I'm still keep my hand in. So I, started my career in my PhD looking at supermassive black holes and the center of galaxies, active galaxies, blazars in this case, this particular class of quasar. And I still do some of that work. So I'm interested in that. I do hope to use our Giant Magellan Telescope before I retire to do some distant galaxy work and distant active galaxy work. So that's what I'm interested in. For as far as astrobiology goes, I'm not trained as an astrobiologist, so I write a lot about it, and I'm a commentator, if you like, and I know enough just to be dangerous, but that's about all.
One more question from Del Gordon. He says, you mentioned UAPs and extraterrestrials in the title of your paper with Ron Joseph on extraterrestrial life in space, plasmas in the thermosphere, UAP, pre-life, fourth state of matter. Have you received any flinch, quote unquote, or feedback from the academic or scientific community because of that paper or the title?
Oh, sure. I mean, I'm senior enough that I don't worry about that. You got to take a few chances when I mean, I hope I haven't violated my academic principles. I was a moderating influence, if you like, on that paper, but I think there's some core data that was very interesting to be reported. And I just tried to modulate the speculation in the paper or make sure it was clearly flagged as speculation. I mean, you're allowed to speculate. Remember Carl Sagan co-authored with Ed Salpeter a paper speculating about buoyant life forms in the atmosphere of Jupiter. And it was published in a peer-reviewed astronomy journal, flagship journal. So, you can do that. It's fine. UAPs is another whole area. I'm not even going to comment on that. They are just what they say. The acronym says it all. They're unidentified aerial phenomena, and people are working hard to figure out what they are. But there's no reason at all, as with UFOs, to connect the dots to imply they're alien spacecraft.
Oops. I'm typing as well as speaking. Okay, so here is the link to our YouTube channel. And be sure to share with your friends this channel because this talk and many other talks are to be found there. And I see Bob is still contributing away. Let's see, Arthur C. Clarke also visited the atmosphere of Jupiter.
Yeah, I mean,
You
an
know,
interesting speculation that there are a lot of, in the people talk about the cryogenic biosphere. The Earth is in the classical habitable zone, the right distance from its star to be water on the surface. But the cryogenic biosphere is a large set of places, typically much further from the star, where water is either kept liquid by being under pressure of rock, and that's the moons of outer planets, or you have a temperate region in the atmosphere of a planet where the base of the atmosphere, like Jupiter, is incredibly hot and high pressure and uninhabitable, and the top of the atmosphere is extremely cold, so far from the sun. So there are temperate zones of the outer gas giant planets, and we imagine similarly in exoplanet systems. So with Sagan and Clarke and probably others, these are quite interesting places to speculate about.
they certainly are. And it's good that we have Bob at this meeting because it's like you're working in counterpoint. You're doing the more science end, and Bob just keeps popping in these. He does nothing but read anthologies of science fiction. So I guess all of this stuff is stored, which is good. Good to have you here, Bob.
Yeah.
Okay, and one thing, next month, we're having the ever popular Tosi Adegbija, who he's very popular with our group too. And he teaches in the electrical engineering department. He's been here 3 times. And before, we move on to anything else, I want to tell you that, June can be a very slow month, but it won't be with Tosi. And this one has been very exciting. And it's good to have back to back 2 really exciting speakers. So I want to really encourage anybody else who has any more questions to ask them now in the chat, or do you want to divulge one of your emails in the chat so people can follow up with you, Chris?
I'm sure, yeah, I'm sure my email. Let me get back to the window. I lost my window.
You're getting an invitation too, it looks like, from Del Gordon.
Okay.
Yeah, he's there inviting you to the Huachuca Astronomy Club.
Okay. So I'll just put my email in here.
Thank you very much, Chris.
Now I'll give a warning though that this is last day of classes Tuesday. I got to get grades and finals. So my response to anything that isn't academic will be very slow for the next 10.
Oh, don't worry about it. I think everybody understands, the end of semester if you're a faculty member.
Yeah.
And there you have it, group. Look in the chat, and you have, if you think, I know how it is. You hear all these, it's so densely packed what Chris has given us that it takes time to process it all. And then you don't really have time to ask some things. So there's his email if later on you want to ask him anything.
Yeah, it's good. Happy to dialogue afterwards.
You're very good as a, well, probably because you're an instructor, you're a college professor, so you know how to communicate and include everybody. That's a good thing. And nobody should feel out of it, even if this is the first time you've heard all these things. It's great because you can always take it up. Now that we have the internet, you can look up all these things. I'll tell you, for 3 days, I was watching nothing but astrobiology and on YouTube. A lot of it was clickbait. Have you heard of Atrium or Astrium? I think it's Astrium.
No.
It's some site on YouTube that does astrobiology among other astronomy topics. And actually, it sounded very well documented. And he mentioned some other chemical, and it wasn't hazeltine. It was something like hezeline. I'm off, but it was and I should have given people that link. I could put it in later. I can send it out to everybody who came. I'll try to find that link. And it had some interesting stuff on it. So any other comments? They don't have to be questions, just comments about what you think of all this. How does it affect you? Were you engaged with the ideas of having these beings out in space? Anybody, does it scare you? Are you thrilled? Do you want to meet them? And we know there's mixed views about wanting to meet them.
Right.
Okay, so people don't want to commit. Maybe they're thinking it over very hard. I can hear them. I knew Bob would have something scary to say. Bob has what we call a dark sense of humor on these things.
Yeah, I agree. Being alone, with so much potential for biology in the universe, if we're unique, that would be extraordinary. And logically, it is possible that, the research on how life started on the Earth is not really tied together enough to show that it's inevitable or has to happen. And you have one example, so you can't make an argument. You can't do induction based on one. So it's certainly possible in the hard step, the great filter argument, that the great filter could be the very first step, going from inanimate ingredients to the first cell or the first living creature. That's still possible given what we know and don't know. And then we are essentially alone.
Well, I want to thank, especially, just so some of you may not know, one of our attendees is actually live from Cairo. That's Imad. And he's come to us. I don't know what time of the day or night. What time is it there, Imad? Is it middle of the night for you?
Gotta be.
8 p.m. That's not bad. So you've reached another continent, Chris, with this talk.
Okay, great.
Yeah, and thank you very much for this wonderful presentation. And I love the visuals. They were so, very effective. A lot of them too.
Yeah, okay, it was good to be with you all.
Okay, so thank you very much. And I guess people are starting to sign off now, and I hope to have you back sometime because, you're always working on new things and we're eager to hear about them.
Okay, well, thanks for inviting me, and
You're welcome.
good night, everyone.